Okay, this lesson comes from section 10.7, and it is about complex numbers. Now, I almost wish they had given them a different name because complex is kind of an intimidating word, but these don't have to be intimidating. As a matter of fact, you have already been working with complex numbers for quite some time, because the real numbers are a subset of the complex numbers. So you have been working with them. All right, so if you wanted to talk about the square root of a negative number, well, we've said this before. I actually said this when we did lesson 10.1. The square root of 25 is 5 because 5 squared is 25. And so when I want to know what the square root of -1 is, or any negative number, we think about answering, and we say, well, is it 1? No, because 1 squared is 1. Is it -1? No, because -1 squared is 1 also. Can you square a number and get a negative? Well, the answer is no. So mathematicians just invented a new number, and they called it I. They gave it a letter name. It's usually written kind of italicized, so I usually just give it a little tail. All right, because now this is just a definition. I squared is -1. And you're going to want to remember this statement. It's a definition. Nobody has to justify it. At some point it was accepted, became part of our math world, and now it is used all the time. Now, that means that so far we've looked at two kinds of numbers. We've looked at numbers that are real. And there's all different kinds. There's whole numbers, counting numbers, fractions, decimals, irrational numbers. They're all real. So like 7, -14, 2.5, square root of 3. They're all real. Numbers that involve I are called imaginary, and they would be numbers like I, 6i, -14i, square root of 3 times I. Okay, remember what's I?
-1.
Square root of -1. It's the square root of -1. Now, all of these numbers fit into one big giant category called complex numbers. If you take the real numbers and you take the imaginary numbers and you put them together, that makes up some of the complex numbers. Some. So what are the other guys? The other guys are kind of hybrids. All complex numbers can be written in the form a plus bi, which means that a real number is complex. Let's say 7. It is complex because it could be 7 plus 0 times I. So it is complex. Okay, an imaginary number like 5i is complex because it is 0 plus 5i. So in real numbers, the imaginary piece is 0. In imaginary numbers, the real part is 0. But there are other complex numbers that have both parts. 7 plus 5i is a complex number. -3 plus square root of 2i. That's a complex number. Complex numbers, which is all the numbers, have real parts and imaginary parts. If the imaginary part is missing, we call it real. If the real part is missing, we call it imaginary. Okay? But they all fit under this big umbrella called complex numbers. Now let's talk a little bit more about it. That was just a little bit of an overview. What if I ask you to express in terms of I the square root of -28? Well, in terms of I, do you agree that I could say it's the square root of 28 times the square root of -1? Okay, now could I simplify this positive square root of 28? Is there a perfect square factor that goes into 28?
4 and 9.
4 and 8. I mean, 4 and 7. We'll get it in a minute. We just keep guessing. All right. So it's the square root of 4 times the square root of 7 times the square root of -1. The order that you write those doesn't really matter. I'll show you in just a second what is customary. The square root of 4 is 2. I don't know what the square root of 7 is. And the square root of -1 is I. Now, I think that what I'm about to tell you is customary because of the way printing presses used to work. The I, in olden times, was never written behind a radical because the way they printed things, it sort of looked like it was under the radical. And to get it far enough away from it, it looked like it didn't even belong. So they started printing with the I always in front of the radical. Okay, so this is typically what you're going to see. The square root of 28, simplified and in terms of I, is 2 times I times the square root of 7. And if you are wondering, does anybody use this stuff? Or is it just mathematicians, sitting in rooms with calculators and computers and they didn't have anything else to do? People use it. I asked the same question. I had to take an undergraduate course. It was like a junior level course that was just over complex numbers. The whole course was over complex numbers. Then in graduate school, I had to take a sequence of 2 courses on complex numbers and how they behave in calculus. It was a little bit mysterious to me some days. I wasn't totally clear on everything that was said in that classroom. And I was working with a physics professor at the time in the summer, and I said the same thing you probably say. I said, does anybody use this stuff? And he said, oh yeah, when we analyze circuit, those are described by complex equations and blah. And I was like, oh, good, yeah. So, yeah, somebody uses it. So we're just gonna scratch the surface. We're gonna get introduced to this set of numbers. And there was a point in your life when negative numbers were mysterious to you. There was probably a point in your life where fractions were mysterious to you. I guess that could have been yesterday, but no. That was supposed to be a joke, a little joke. People just don't tend to like fractions too much, but just a joke. All right, so we're going to try to just accept, okay, this is just one more thing. Maybe you've been exposed to them, maybe you haven't. We're going to try to get used to working with them. It says express in terms of I, the opposite of the square root of -25. Now, I don't want to always have to factor square roots of negative numbers into the square root of the positive number times the square root of -1. Can we just agree that if we're going to take the square root of a negative number, I is going to be part of the answer? Okay, so this negative sign goes with it. What is the square root of -25?
5i.
It is 5i. The square root of 25 gave me the 5. The square root of -1 factor gave me the I. And that negative sign was out in front. So if you had wanted to, you could have said it's negative square root of positive 25 times the square root of -1, and that would have given me negative 5i. Okay, that's where all the pieces came from. Anytime the radicand is negative, that means the answer is imaginary. All right, number 3. Write in terms of I, 3 times the square root of -175. All right, keep the 3. I'm going to need a square root of -1. Now, can you break up 175 into 2 radicals? What's a perfect square factor? 25. And it's 25 times 7? All right, now I'm probably going to have to rearrange these, but let's just take all the square roots that we need to. I'm going to keep the 3. The square root of -1 is I. The square root of 25 is 5 times the square root of 7. I don't want to leave the answer like that. How should I write the answer?
15i?
Yes, 15i square root of 7. All right, number 4. It says, write in terms of I, negative square root of 175. Well, is this going to have I in it?
No.
No, it's not. So we're going to keep the negative. We probably would not actually redo this part because we've just worked with the square root of 175. So that's going to be -5 times the square root of 7. Now, I want to make sure it says express complex numbers in terms of I. Oh, okay. This is a complex number, but I'm pretty sure they don't want us to have plus 0i. But, Ann, do you have the answers printed? This is number 4.
6.
Oh, I was like, well, if they got 6, they're doing it differently than I. I should have my own.
-5 square root of 7.
That's all they have. Okay. All right, then that's fine. They just threw in a real number, I guess, to see if you were going to fall for the trap that a negative on the outside would make it be imaginary, and it's not. All right, so do you have sort of a sense of the value of I and where it comes from? It's the square root of -1. All right, now that we've sort of met the complex numbers, well, let's see. What have you always done with numbers that you learned about? Well, first you learned about the numbers, what they meant. The next thing you did was learn how to add, subtract, multiply, and divide them. And that's what we're going to do. We'll start with addition and subtraction. You're going to see a lot of similarities between working with complex numbers and working with polynomials. As a matter of fact, working with binomials, because there's going to be 2 terms in these. All right, number 5. it says to add. It has 2 plus 6i, close parentheses, plus parentheses, 4 minus 5i. I have a complex number. It's got a real part and an imaginary part. I've got another complex number, real part, imaginary part, and I'm going to add them together. And what do your instincts tell you you should probably do?
Like terms.
Yes, combine like terms. And we've got the real parts, and we've got the imaginary parts to add up. So I have 2 plus 4 is 6 for the real part. I have positive 6i and negative 5i for
Negative I.
positive I, because the 6 was bigger. And that's my answer. If you were to actually major in math, and one of the courses that you would take would probably be about number theory. And in number theory, one of the things you talk about is with these sets of numbers that we've talked about today, the real numbers, the rational numbers, the integers, all of that, they always have to have closure under certain operations. Now, closure means that if you add a complex number to a complex number, you get a complex number. So it's closed. That means that if you do this operation, you get another member of the set. That was for free, you know. All right, number 6. It says to subtract. I have 4 plus 7i, subtraction sign, negative 4 minus I. Well, what do you do with subtraction when you're dealing with polynomials? Yes, change the signs. I'm going to keep the signs on the first one, change it to addition, and change the signs in the second complex number. So you do just what you did with polynomials. You could think of it as distributing a negative 1. So now I'll add the reals. 4 plus 4 is 8. I'll add the imaginaries. 7i plus an implied 1i is 8i. And I'm done. And anytime you subtract two complex numbers, you get a complex number. Typically, when they give you one that's got the two pieces to it, typically they put it in parentheses, but you don't have to put your answer in parentheses. Number 7. Little more subtraction. It has the real number 4 minus parentheses 15 plus 5i. It's subtraction, so what do we do? Change the signs. Keep the 4, change it to addition. That'll become negative 15. That'll become negative 5i. So now I still combine the real parts. I have a positive 4 and a negative 15 for negative 11. And I don't have any other imaginary term, so I'm going to have minus 5i. You could call it plus negative 5i, but I like to avoid double signs. All right, next we've added, we've subtracted, and now we're going to multiply. Multiplication, we're going to look at distributive property, we're going to look at FOIL, we're going to look at all those things, but let me call your attention to something that I blocked in on purple. Up here in purple, I said, you really need to remember this. Now, we worked using that the square root of negative 1 was I when you simplified some radicals. Now we're going to use this part. Anytime you see I squared, you can replace it with a negative 1. Okay, so just keep that in mind. All right, number 8 says to multiply negative 3i times negative 4i. Well, the commutative property of multiplication says that I can move these four quantities that are getting multiplied, because it's a -3 times an I times a -4 times an I. I can move them around if I want to. So in my head, I'm going to multiply the -3 times the -4, and then I'm going to multiply the I times the I. You don't need to write that down, but that's what's going on. So the coefficient will be what? Multiplying for 12. And what's I times I? I squared. But we don't ever leave an I squared because we know it has a real value. What is the value of I squared? -1. So this is 12 times -1, which is -12. The product of those two, imaginary, which is a type of complex number, gave us a real answer, which is a type of complex number. So when you multiply two complex numbers, you're going to get a complex number. Number 9. I have 9I parentheses 7 minus 3I. What kind of multiplication am I going to use? Right, distributive property. I have 9I times 7 would give us 63I, and I have 9I times -3I is -27I squared. But I'm not going to leave that, because what do I do with I squared? Make it become a -1, and -1 times -27 is positive 27. So I have 63I plus 27. And typically, when you write a complex number that has both parts, you put the real part first, 27, and the imaginary part second, 63I. Now, what I'm going to be doing in the future, when I have 63I minus 27I squared, what I'm going to do is just mark through the I squared and change the sign of the term. Because that is what happens every time. I squared is -1. You multiply it, it's going to change the sign. Okay? Let's go to 10. I need to multiply 6 plus 5I times 6 minus 5I. Anything special about that product?
Difference of squares.
Okay, we're going to get the difference of squares because this is a sum and a difference product. If I represents the square root of -1, it represents a radical, then what could you say these two expressions are? What's their relationship? They are not opposites, close, conjugates. We saw conjugates yesterday when we were rationalizing denominators, but those radicals represented real numbers. I know these are imaginary, they're still radicals, so it's still appropriate for us to call those conjugates. All right, let's multiply and see what happens. What's the product of the first? 36. Now, tell me what you recognize will happen with the outers and the inners. They'll cancel out. There's no point in doing them. So, product of the last. It's a positive times a negative, so it's -25I squared. And we don't leave I squareds, do we? Nope. So get rid of that and change it to plus.
Do the signs not change on those? Because I'm doing the homework,
Uh-huh.
and on the example, it changed all the signs on,
Was it subtraction problem?
yeah, it was Oh, to the subtraction between the two parentheses. Okay.
There you go. That's okay. All right, so since we're multiplying, we're going to get a 61. What you're going to find out is that the product of complex conjugates is always equal to a real number. And it's a real rational number as well. Conjugates are important. Let's look at 11. I have parentheses, -7 minus 3i quantity squared. Well, why don't we just practice and see if we can square it the way you can square a binomial. We'll try the shortcut, and then if you don't like it, I'll do it by FOIL. But the product of the first, square it. What's -7 squared? 49. For the middle term, you multiply these two. -7 times -3i is 21i. But what will the middle term be? Yes, 42i, because it's always double. That represents the inner and the outer product. And then when we square the last one, -3i times -3i will be positive 9i squared. Okay, so I'm going to say, I'm not going to leave that as I squared. That is now going to become a -9. So I have 49 minus 9, that's 40, plus 42i. When you square a complex number, you get a complex number. Now, you could have said -7 minus 3i times -7 minus 3i. The product of the first is 49. The outer product is -21i. The inner product is -21i. Those combined together, those were both positive, weren't they? So much for my signs today. Plus 42i. The product of the last was plus 9i squared. And then I would finish up the problem. But it's a little quicker to do it as a squaring a binomial if you just remember how to get the middle term. This is always your fallback. All right. It's time to divide. Well, we're not really going to divide, but we are going to rationalize the denominator. It has 2 over 7 plus 9i. Well, I call it division simply because there is a fraction line. Now, I'm going to rationalize the denominator. Based on yesterday's experience and the little bit that we've said today so far, what are you going to multiply by? The conjugate over itself. So 7 minus 9i, 7 minus 9i. So there's a strong relationship between what we're doing today and what we did yesterday. The numerator, what kind of multiplication will that be? Distributive property. 2 times 7 is 14. 2 times -9i is -18i. Now, the denominator, when you multiply conjugates, complex conjugates, what do you always get? A real number. You always get a real rational number. So, 7 times 7 is 49. 9i times -9i is -81i squared. Can't leave that, can I? That's gone. It becomes a positive. 49 plus 81, I believe, is 130. Now, let me say something about the answer. It says simplify your answer. So if all terms, because remember this 18 is being multiplied times the I, it's like an 18 times a radical. If they all share a common factor, you need to reduce. What will go into all of those? 2. All right, so, whoops. 2 is going to go into 14 7 times. 2 goes into negative 18i, negative 9i times. And 2 goes into 130, 65 times. There's one other thing I have to do. It says type your answer in the form A plus BI. Do you remember that I said real early in today's talk that all complex numbers can be written in the form A plus BI? Well, all you're going to have to do is break this into 2 pieces. You're going to get 7 over 65 minus 9 over 65i. And you will find, I haven't said this, I should have, you will find the I, that italicized I, over in the toolbar. I don't know what it would do if you typed the I off the keyboard.
It still works.
It still works. Okay, now I know. You can use the toolbar or you can type the I off the keyboard. Thank you. If you were taking a test for me, this answer, paper pencil, would be just fine. But you're going to be taking an online test, at least when I'm recording this, the class I'm talking to is taking an online test. And so you have to put it in the way you'll do it in the homework. All right, number 13. I have 5 plus 7i over 1 plus I. And I have to find the quotient. All right. What will I multiply by? Yes, 1 minus I over 1 minus I, the conjugate of the denominator. What kind of multiplication will you be doing with the numerators, with the tops? FOIL. And I just put them in parentheses because they look more like binomials if I do that. So, what's the product of the first? 5 times 1 is 5. The outer product is a 5 times a negative I, or negative 5i. The inner product is positive 7i. And the product of the last, I have a positive 7i times a negative I gives me negative 7i squared. What shall I change? The I squared. All right, I squared goes, which makes that now a plus 7. And I have like terms here with the outers and inners, don't I? So I'm going to go to another line, and I hope it doesn't confuse you that I'm completely finishing the numerator before I look at the denominator. So I have a positive 5 and a positive 7 for the real part of 12. Then I have negative 5i and positive 7i for plus 2i. Okay? When we multiply the conjugates, the product of the first is 1. 1 times 1 is 1. The product of the last is negative I squared. All right, now there's no coefficient in front of it unless you call the implied negative 1 its coefficient. So, what's the opposite of the square root? what's the opposite of I squared? Well, it is the opposite of negative 1, which is positive 1. So what is the denominator? It's 2. Can I simplify this fraction? Yes. We look at all of the rational numbers and rational coefficients, and we say, yes, common factor is 2. So this will end up being 6 plus implied 1i over implied 1. And I'm done. All right. We want to talk for just a minute about the powers of I. Now, this is really, from a math standpoint, this is really interesting. From an everyday standpoint, maybe not quite so much. Take a real number. Any real number except 0 or 1, because they are definitely special. I'm going to pick something small, 2. Okay? 2 to the first power gives me 2. 2 to the second power gives me 4. 2 to the third power gives me 8. And so on. Do you agree that there's going to be an infinite number of different values as you raise 2 to powers? And that happens for all real numbers except 0. 0 to any power is still 0. 1. 1 to any power is still 1. So with those two exceptions, it grows. Sometimes it shrinks. Do you ever think about that? You raise numbers to higher and higher powers and they shrink? How about the fraction 1/2? To the first power, it's 1/2. To the second power, it's 1/4. That's smaller. To the third power, it's 1/8. Smaller. So when you raise proper fractions to bigger and bigger powers, they don't grow, they shrink. Okay? And that was just so that you think about what real numbers do. Now, let's talk about imaginary numbers. And then I'm going to give you a shortcut. Okay? But, all right, I to the first power, it's I. I to the second power, it's -1. I to the third power, well, I don't know. Could I break I to the third power into I squared times I? Is I squared times I to the implied first power equal to I to the third? All right, and that's going to be a -1 times an I, which means that I to the third is equal to -I. I to the fourth. I don't know. Well, I do know a few things. I know I squared. So could I call I to the fourth I squared times I squared, which is -1 times -1, which is +1. Well, it looks like the powers of I are just all over everywhere. All right, how long am I going to keep this up? I to the fifth. Well, you know, I really like I to the fourth because it's equal to 1. So I'm going to say that I to the fifth is I to the fourth times I. Since I to the fourth is 1, it's the identity, can I just ignore it? Yeah. And that means that I to the fifth is the same as I. I to the sixth. I like I to the fourth because it's 1. And what would the other power of I have to be? I squared. Okay, I know this one is 1, and I know this one is -1. I multiply those for -1. I promise I'm not going to keep this up forever. I to the 7th. I'm going to call it I to the 4th times I to the 3rd. I to the 4th is -1. I'm sorry. 1. I to the 3rd. Oh, let me see. I already did that. -I. So it's equal to -I. Now, we'll do one more. I to the 8th. That's I to the 4th times I to the 4th, which is 1 times 1, or 1. Now look and see what's happened. It went I, -1, -I, 1, and then it went I, -1, -I, 1. Those are the only 4 values that I to any power can be. That's it. Those 4. So if you could remember the first 4, or recreate them if you forgot something, you could find I to any power. Now, I'm going to show you the long way to do this, and then what I think is a shortcut. Number 18 says, find the powers of I. I to the 39th power. All right, here's what you can do. The powers of I are, it's going to be an I, -1, -I, 1. Those are the only 4 possibilities, right? And I wrote them down in the order, I to the 1st, I to the 2nd, I to the 3rd, I to the 4th. So you can, if you want to, do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39. Oh. There's my answer. Okay? Now, that works fine unless I ask you to find I to the 5,927th power. And then you'll get a little tired of 1, 2, 3, 4. So, I don't know that you really observed it, but maybe you did. Every time I went 1, 2, 3, 4, then I started over, 5, 6, 7, 8. 8's a multiple of 4, isn't it? And then I started over. 9, 10, 11, 12. 12's a multiple of 4, and I started over. Which means every time you've got 4 powers, 1, 2, 3, 4, it's as if they didn't even exist. And I slowed down a lot after I got to 36. And then I said 37, 38, 39, because it's that last cycle that tells me what it's going to be. So here is the shortcut. Take the power, divide it by 4. 4 goes in there 9 times. That's 36. Subtract for 3. That means 9 times I will go completely through the cycle. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. 9 times. And what counts is the remainder. So I to the 39th is the same as I to the 3rd power, and you're going to know those 4 because it goes I, -1, -I, whoop, there it is, 1. So you're saying all those cycles of 4 don't really matter, it's just the leftover. The area of math that we're kind of talking about where you just get a finite number of answers and then you start over with it, it's called modular math. you study it for the first time in your whole life when you study the clock. Because you go to 12 and then you start back over at 1. So there's a whole study in number theory of modular math. And I know y'all so appreciate me bringing those things up. It makes my day more interesting, so indulge me. All right, I to the 9th power. If it's a small power, maybe it's worth it to go 1, 2, 3, 4, so on. But showing you the shortcut again, what do you divide by? 4. It's going to go in there twice for 8. Subtract for 1. That's the only thing I care about. I to the 9th is the same as I to the 1st, which is I. Is that okay? And number 20 is not much of a challenge. I have I to the 7th. Without even doing a division problem, I to the 7th is going to be the same as I to the what? 3rd. Taking out 4 of them, which is negative I. Okay, so you know lots and lots about complex numbers. When we do the portion of chapter 11 that we do, we're going to find out that some of those quadratics that we couldn't factor them because their answers might have been irrational, meaning they had square roots in them, or they might have been complex, meaning they had i's in them. That's why we couldn't do it by factoring. So that's what's on store for Monday. All right, end of this.